Hey, welcome to the Lux channel. So I see this confusion often among anyone who starts learning system software programming, and they learn various concepts, and eventually down the line they start learning about kernel components and OS basics. And along with that they start also learning about various subsystems in the operating systems, like process and memory and stuff like that. And along with that they start also learning about synchronization concepts, and this synchronization can exist in a database, it can exist in a process, in an operating system level, or in the kernel space, and as well as it can exist in the user space. But end of the day they fully get confused, and it is not a mistake on your end. I often see in the college also they often make a huge fuss out of it, and it's the confusion what your tutors have is put on to the students, and eventually if you go through the books again you will get confused, because synchronization is a vast topic. So once you start exploring, the author of the book can give any examples, but you should understand, is it something he's specifically mentioning about something about a OS inside the operating system, or something in the user space level or something. So as a part of that, I thought this episode, let me cover a very basic user space level synchronization between threads, because you should require a sort of synchronization in a thread, because the thread shares a common memory space, because all the threads do exist in a single process. You should understand, whenever you create multi-threaded processes, all these threads will exist in a single process, and they share a single common memory space among them. So this is something I covered in various episodes. Especially I covered the same in an episode called process versus threads in the systems architect perspective, because this is not some episode I want to shoot what a process is versus what thread is. It is little bit advanced. I recommend you can go through that video episode along with this, so that it gives that big picture. Always I discuss my episodes a bit higher level, so that it completely gives that full big picture, not just talking some or covering some basics or something like that. So just come out of the shell and try to see that big picture. So if you see that way, threads do exist within a process, and these threads, as I said earlier, will share a common memory space. So in case if one thread crashes, which essentially means in case if one thread crashes, of course it is going to kill that process. So the entire process will get going to crash, and it is going to bring down all the threads. Same way, if you have multi-processes versus multi-threads, and each of these processes don't have any threads, let's assume if any process crashes, the other process is going to still work, and if the kernel crashes, then all the process is going to crash, and the entire system is also going to crash. As simple as that. So don't confuse about all these terms, and don't complicate yourself. It is quite very simple. So anytime if the kernel crashes, of course your entire system is going to crash, and you need to reboot your system, versus if the process crashes, and you can if it exists like a sort of defunct, or or else it hangs or something like that, and then you can kill the same. And if any thread crashes, of course because it is sharing the common memory space, it is going to bring down the entire process. So let's not confuse about all these things, because this is something you need to understand. Even for synchronization, it is very simple. As you can see here, I have done a very simple sample code, one without synchronization, the other with synchronization. So as you see in my code, most of my episodes, even this code, I'm going to share it so that below this video episode I'm going to share the link where you can go and you can download it, and then you can experiment and you can play around. So this is something a basic code. One thing I would like to mention, unfortunately when students learn or anybody learns about all these concepts, they see some sort of useless code like this which doesn't do anything in reality. So you can see here it is just a dummy example. Their entire life, as long as they see the books, as long as they see any examples in the internet, they see this kind of useless dummy code which says that okay, you have a thread creation and you have another thread creation and do what. And in the example they put some kind of code like this. Even in my example I put a code like this without doing any sort of real work. So for this I'm going to show you my Toffee code, Toffee data center code, so that I can show a little picture that how a real code looks like, so that you can jump back and then you can take this as an example, because that is something very difficult to understand. So this is something I can't take a Linux kernel source like I do in most of my episodes. So let me show my other code. So you can see here this is my Toffee data center code, which is what you can download in the Toffee project website. So if you see here, you can see here this is the code, and you can see here even this have threads, and this is a little simplified one. Earlier it used to have many threads, but currently it doesn't have any more threads. You can see here it is just having sort of one thread. I can even remove that. I just kept it because if in case if I add any simultaneous tasks, I can just put inside. Please bear in mind, although I said tasks, this is not any operating system task. What I'm saying is any particular job, if I need anything, a classified job, a set of operations or set of batch processing, I can put its respective threads to handle it simultaneously. So I used to have many such jobs, and as I refined my code and as I moved my code from the Toffee to the Toffee data center stuff, I have removed many such components. So eventually it has only one thread, and even this can be replaced. I can even bring this infinite while loop under here. So you can just ignore the purpose. As I said, there are two things to do or look this fact. As an architect, I put certain things as a part of architectural decision, but as a part of a student who learns about programming, you just need to sort of understand that what you are seeing is a real code. This is not any example code, and I can do anything as a part of its architectural perspective. So it's my way of doing things, and I put whatever I want. So don't much focus on what exactly I wrote. Just let's focus on what is that you can grasp out of a real code, something like this. So if you just hop on to another daemon, you can see here in this folder I have many daemons, and here you can see this is the daemon called as R, and this is once again Toffee data center R. So this daemon, if you see here, it has couple of threads. One is LAN thread and one is WAN thread. So that LAN thread handles the flow from packets from LAN to WAN, and WAN thread handles flow from WAN to LAN. So you can see here it has just two threads. So if you see here, it has two threads, and inside two threads it has many sockets kept open. So this is how the real code looks. And in case if you have seen even as socket coding examples, they just write one UDP socket, UDP client, and then some TCP socket and TCP client, and then they say that's the socket code. But in reality, somewhat like this is what a code looks like. So in the thread function, you can see here, this is my thread function, LAN thread function. In the thread function, I have many sockets, and I have many sockets for various cases. And sometimes I'm also doing, in this case, a sort of load sharing. So I have even more sockets like that. So same way in the case of WAN thread, I don't need to do that. So I have a different logic here. So it's really damn complicated. So this is how the real code looks like. And same way, if you see the transmit, you can see this is the code, and here you don't find those many sockets, but again this is a thread function. So why I am saying that is, this is how the real code looks like, and you need to see the relationship between your example code to a real code. I don't want to give some useless example code, and this is the same example code, you will find it in a book. Then what is the use of me shooting this video episode? And anyway you can find tons and tons of such YouTube videos, so why I should shoot once again a beginner video? So that is the reason I thought, let me give that big picture. Always Linux channel I focus about advanced system architects, and it's all about the big picture of doing things, not sitting with the basics and wasting your time. So that's the reason I'm showing my code, so that this gives that full big picture. This is how the real code looks like, and in this, if you have any common shared resource, then it is going to create a problem. In my case, always I architect in a way that I avoid synchronization, and this is the disease I find many times when I was working in full time. Whenever I attended an interview, they ask always about synchronization and all this bullshit questions. The reason is, they may think it is very vital as a part of software architecture, but if you see my way of doing things, I generally completely avoid that. If you see my code, I never do anywhere synchronization, because I do a different type of architecture. To avoid such cases, I can do some changes in my architecture so that I have I don't need to do any sort of synchronization, and I don't have any sort of common shared resource and stuff like that. So it's again a sort of it's a difference between a programmer versus how do you creatively architect your stuff. So there's a lot of difference. So this is something you should learn, but whether you implement in your code or in your lifestyle is your choice. But if you ask me, I'm not a big fan of using any sort of synchronization unless until it is just seriously required. And if you see my old Traffic Squeezer or Toffee code, of course I have done with some common buffers with spin locks and stuff like that, but again it's just required as a part of its basic necessity, so I have done it. Otherwise I'm not a big fan. And some spin locks I have even replaced with atomic constructs. With that, again I simplified the code. So again it's a part of architectural decision. So if you are just a student just starting these things, just keep in mind that no one is forcing you to use all these concepts. With this hope this gives a sort of big picture. This is how a real code looks, and let us hop on to a very simplified example code which I am going to share with you guys, so that you can download it from this YouTube description link. So if you hop on to my example code, as I said, I have these two user space applications. So one is without a thread, and the other one is with without a synchronization or the mutex. The other one is with mutex, and this is the compile script. I never use makefiles. I don't like writing any sort of makefile, so I just write always a static compile file, so that it is very easy to edit, and it's just a simple bash script. So if you go to the user space, if you go to the CLI, and I did some trials before shooting this video. So what we can do is we can run this example pthread sync via mutex. So ls, you can see here it has compiled, or else you can just compile the same. So once you download the code, if you want to recompile, you can use this compile script, so it can compile both those source code files. So let us run pthread. Before even running without, better to run this sync via mutex. So if you go through the source, before running, better I can walk you through the source so that you will understand. So if you go through the source, it is fairly very simple. After all the basic include files, you have this two pthread instances. I am little describing because in case if you are a beginner, you can easily grasp. So you have these two pthread instances, and below is this mutex pthread mutex instance mlock. So after that I am defining a large hash define with 1,000,000 bytes. So anytime you do some examples, if your system is quite large, do something like this so that it puts some sort of a load on the system. Because of the load you can see different behavior. If you don't put enough load, you may not see the desired effect. So it's always good practice to put some load whenever you do even test socket applications. Whenever you learn socket applications, do something like this so that it mimics the real world cases. I often see that whenever they do programming, they just put some 10 bytes or 100 bytes. It's not like that. So in a real world situation, you may need even a 1 GB of space or 1 MB of space. So be realistic. So I put around 1,000,000 bytes. So you have a buffer with 1,000,000 bytes. And below the main API, you can see it is very simple. We are initializing that Mutex with this API, Pthread Mutex in it. This is the API to initialize. There is nothing fancy about. So if it is returning any value, then it has an error. So I am displaying the error. And below that you can see here with Pthread create, we are creating or initializing these two thread instances, T1 and T2, and these are its respective thread functions. So you can have something like that, and in case if it is not successful, you can display some error. If you compare it with a real code, in fact you can see there is a lot of similarity, because I always have a practice of doing any example which even mimics a real situation. So you can see here this is as straightforward, even the real situation I am doing the same thing, you can see here. So this is what I'm doing here. Similarly, you can see here this is what I have done. So you have two thread functions, and we are just initializing those two threads. So with that it is done, and you can add that pthread join and stuff like that. So it's very simple code. If you go up, you can see here the thread function contains a big infinite while loop, and don't be scared of using while loop whenever you do a proper research. So that again it puts a load on the system. Don't use some kind of a loop with just 10 iterations, 3 iterations or something like that. Be liberal whenever you do any buffer initialization. This is again a disease the industry got. They think memory optimization is the best in this world. So be liberal and mimic a real world situation. So do an infinite while loop so that you can see as it gets loaded how its performance characteristics changes. So this is something is quite more fun if you do in a small device like Raspberry Pi or something, rather than a huge system like mine. So there you can see a different type of performance curve versus a system like this. So it is quite interesting. So you can see here inside I'm binding this the main task within this Pthread Mutex log. So with that we are restricting so that whatever you are doing inside is synchronized. So you can see here memset, I'm doing a memset of this buffer, and I'm setting some random bytes like AA with this 1,000,000 bytes of size, so that the entire buffer is done memsetted. So you can see here this is the buffer. If you notice one important thing, you can see always if the code needs or the flow of the code needs synchronization, you can see here this is the sort of common resource, and inside the common thread function, that common resource can be accessed anytime by these two APIs. So anytime both the APIs can touch that common resource, and this is where you need the synchronization, so that when one particular thread function is holding that, the other thread function should wait, and it should wait for its turn. So if not, then you are going to get some kind of garbage or garbled results. So that is what is essentially happening. So before doing a memset, I am binding it with this or encapsulating with a mutex lock, you can see here, and I am passing the pointer because this is the M lock and you need to pass this pointer. So that's how they have done the library APIs. You just need to do the same thing. So pass the pointer, lock and unlock, and inside it I am doing a memset, and after that I'm just printing some few bytes, like 40 bytes on the screen, so that we can debug. So this way it is easy to debug and easy to see visually what is happening inside. So same thing I'm doing in the thread2 function, but in this case I'm doing a memset with BB, so that we will know it is happening in which memset, whether it is thread1 or thread2. So that's what is happening. And after that you can see here it has this usleep. You can even remove this usleep and you can do some trials. You can increase this usleep and you can do some trials. Don't put sleep of 1 or something, because it's too less, and you don't need synchronization if you do. I mean, you may need, you need always, but sometimes with sleep of 1 maybe that condition may not appear. So once it is done, it is going to repeat the same thing again and over again in that iteration. So that's what, if I run this binary, you can see here, let me just stop the same. So you can run it for some time, and again I'm saying this is a fun stuff. If you have a Raspberry Pi or some old laptop or something, you can do this trial. So you can see here it is coolly working. It is running this thread and then this thread and this thread and this thread, and everything works fine. So this way we can confirm that synchronization is happening properly, and we don't have any such race conditions. And one more interesting thing is, since we cannot print all that 1 million bytes, you can do some kind of MD5 of this entire buffer, and you can dump that MD5 signature, so that you can confirm if there is any memory corruption. Without synchronization, you know that somewhere in that bytes of that buffer is garbled. So we cannot print everything and we cannot do a comparison of entire stuff. So that is where you can do MD5 hash or something like that, so that you can check what is happening behind the scenes. So next we can hop on to this example without synchronization. In this example it is quite straightforward. We don't have that mutex, and everything is the same. You can see here, and here as well in the main you don't have that mutex initialization, and rest it is the same. So you have such 2 thread functions, and it is just going to use this common resource, this buffer. So this is our common resource, and it is going to use this common resource simultaneously by those 2 thread function APIs. So you should also notice entire stuff is happening within the same process context. So you never have any other crash or any such situation, because it is all happening in the same user space process context. So it is one process, and it is a common process shared resource. Of course this buffer of million bytes is going to stay in its virtual memory, so it is also going to stay within the same process. So that's what it is. So we can run this example, ls./pthread without sync. So if you run this, you can see something interesting. So you can see here there's a lot of let me just scroll it up. You can see here there is somewhere this BB ended, and then suddenly this A started, and then you can see there is some kind of pattern here, and here suddenly this \n appeared. So this is what is exactly happening, because we are getting that race condition, both is happening simultaneously, and the buffer is getting changed sometimes here by one thread function and sometimes there by another thread function, and it is getting overlapped, and that is why you can see this type of an output. So you can see here somewhere here A ended and suddenly this BB started. So that is exactly is what is happening without the synchronization. It is very simple. So you can see here entire thing is bound within that while loop. So its entire thing is dumped on the screen one shot within that while loop. So we are not doing any changes in that aspect, but the big confusion is happening because this buffer is getting that memset without any sort of synchronization, and one place it is doing a memset, the other thread function may be displaying it on the screen, and this is what is creating this kind of garbled output. So this explains how synchronization is required in a multi-threaded user space context, and this is something live you can see, and assume this is your this buffer is your graphics screen buffer or something like that. It is going to produce some kind of garbage or garbled image or something like that. So this is very important whenever you deal with multi-threaded user space applications. And the applications can be very complicated, like I showed my Toffee data center code. Having said that, once you master these concepts, you can put it in any such real-time applications as and when it is required. It's just you have learned, don't go and put it on everything you design. It all depends on what type of application you are doing. It all depends on, as a part of its requirements, what is exactly required. So use your common sense whenever you move ahead in your career as from a basic programmer to an architect level. You have to take much more decisions beyond just thinking about these things. It's just not about putting these things in everywhere you write. It all depends. When it is required, you can use something like this, and then you can incorporate the same. And of course, even synchronization, you can have various types. I don't want to discuss this something like that in this episode. So hope you guys loved watching this video. If you have anything to discuss, be in touch via mail, and in case if you are interested, you can even join classes and do research with me. So thanks a lot for joining me. Stay tuned. Have a nice day. Bye bye.